Any questions? So, yesterday I was discussing, I it slipped to follow through that discussion. Uh, we were discussing about the nature of the bending moment in gravity load and earthquake load, and I had mentioned that the moments in the beam that you have due to these lateral loads, they are offset, they are countered by the corresponding or similar moments or counteracting moments on the columns. This is very much different from what you observe in the case of gravity loading, where the moments at the end of one beam is counterbalanced by the uh, uh, other end of the adjacent beam, which meet at a column, and they tend to balance each other. But in the case of lateral load, the beam moments are to be countered by the column moments. And therefore, it is important that the dimensions, the actions of beam and column have to be very complementary, and they have to participate in the load resistance together. And as far as possible, it should be uh, adhered to. We should always strive for avoiding beam width exceeding the column widths, right? So if this is the beam, uh, let's say this is the column section that comes, so the beam, let's say this is width of the column, and I will, let us call it h of the column. Now the beam can be, should ideally be of the same, it should merge seamlessly into the column. Then obviously there is no problem with reinforcement continuing through the beam column junction and continuing across to the other end, right? So this is what, but at the most you cannot have, I mean you can at most have beams right. So BW should not be, should be less than beam column plus half of 1/4 on each side, this depth of the column, right? So maybe this can be HC by 4, and this can be HC by 4. So total beam width should be less than, please excuse me, I'll join you in a moment. हाँ sir, hello, hello, जी sir, yeah, हाँ hello sir, yeah. Oh, consensus, अच्छा. हम्म. हम्म. हाँ, ठीक है, ठीक है, मैं, ठीक ठीक. Okay. So the beam width should be at, we should always try to be keep it as of the same size at the column, but if the flexural rigidity demands that it cannot be met, and uh, it is required to extend the beam because of some other architectural or functional reasons, then the beam should be uh, less than this, and in no case it should be small, it should exceed twice the depth of the in the transverse direction, the column size. So this criteria has to be adhered to in the proportioning of the beams to ensure that adequate resistance, adequate complementarity of the action between beam and columns in resisting earthquake load can be adhered to, can be achieved. And of course, similar considerations apply for columns also. Although it is possible, it is not that much critical. Column size can exceed beam size. So the other condition could be when the beam width is like this and the column is somewhat larger than the beam width, right? The depth of the column is much larger than the beam width that is framing in. This also needs to be avoided because the reinforcement, column reinforcement that is beyond this, that is away from this beam line, these are not as much effective in resisting flexure, in withstanding in the flexural resistance as the reinforcement that are column reinforcement that are in the core of the within the dimensions of the beam framing in, beam width framing into the column. So the efficacy, the effectiveness of this reinforcement, longitudinal reinforcement in the columns outside this beam width, that is not as much effective as the longitudinal reinforcement that is available inside this beam width. So this has to be looked at, and as far as possible, beam width should be same as the column depth, so that the joint, the construction happens seamlessly, the joints happen seamlessly, and if required, column widths can exceed, column depths can exceed the beam width, but the flexural resistance, the reinforcement away from the beam width will not be as effective in flexural capacity, generating the moment resistance in the columns as effectively as the reinforcement in the within the width of the beam. So that was the basic idea behind discussion of this difference in the load pattern and the moment pattern that you have. But coming next to rest of the things, as I said, flange action, effective flange width needs to be taken, and it has to be accounted for in calculating the moment capacity, and accounting for the overstrength that is there in the design. The capacities of the column have to be determined accordingly. So first is the accounting for the flange effect, and second one is the provision of the overstrength because of various sources, various factors that we have discussed earlier. So the actual strength is that is provided in the section is actually more than what is uh, aimed at target strength, and the column capacities have to be more than the actual capacities, the estimate, the overstrength, accounting for the overstrength. And that is how it will be possible to avoid development of plastic hinges in the columns, and limit the development of plastic hinges in the beams. And then in beams also, we try to uh, put or locate the plastic hinges away from the beam column face to avoid yielding penetrating into the beam column junction, for uh, which may lead to bond deterioration and may compromise the strength of the beam column joint, the shear strength. And because that will affect, I mean, if the bond deteriorates, then the shear strength of the concrete in the beam column junction will get adversely affected, and that will compromise the stability of the complete frame. So coming to the that is for the flexural design. Rest of the things are pretty simple. Normal flexural design theory applies as long as we take care of these provisions that are required to be observed for earthquake resistance and energy dissipation, building in energy dissipation capacity. One more thing that I mentioned was the shear confining steel is more because of the need to increase the ductility, curvature ductility in the section, then the shear strength requirements. That said, uh, shear strength requirements also need to be adhered to. Of course, it cannot be left on chance. You need to check for the shear capacities and shear strength, whether there is adequate shear strength available, particularly in plastic hinge region where there is severe degradation and severe elongation, and bond may not be as strong as in the elastic behavior. Then shear strength of the concrete cannot be relied on, cannot be relied upon, and the total shear resistance has to be catered by the transverse steel or the shear reinforcement. And also, if you look, these are the, I mean, transverse steel is only vertical reinforcement, and it may and this steel, obviously it has yielded, longitudinal steel has yielded in the plastic hinge region. Then it develops this particular thing may also develop a tendency of sliding shear, because this metal, this tension steel is now in the plastic flow range. It is flowing plastically, so it offers absolutely no resistance, and the concrete here is obviously is already compromised. So there may be possibility of sliding shear happening here, I mean failure by sliding shear. And in order to provide protection against that, it is also recommended that some reinforcement, some transverse, some shear capacities should also be built up by bending these bars by 45 degree in both the direction. Bottom bars should come to top of end, and top end bars should go to bottom end, so that this diagonal steel will prevent, will arrest any tendency for sliding shear, right? Because this vertical stirrup, the straight stirrup, 90-degree bend, they will not offer any resistance to the sliding shear. Only the bent up bars would be providing the resistance against sliding shear. So what are the shear? So what is the shear force that we need to design for? As you can see, for the earthquake load, the bending moment is a straight line from negative moment here to negative moment here, and there is it's a straight line, so it leads to a constant shear force. So the earthquake shear force due to earthquake is going to be constant. Let me just, so this is the shear force diagram because of the earthquake effects in the beam. And of course, for the uh, gravity load beam, gravity load behavior, the shear force diagram is going to be like this. So at the point of maximum positive moment, dm by dx is going to be 0, and that's the shear force vanishes at the midpoint, and it varies linearly through the span. So when we combine these two, then obviously it has to it will add to uh, more shear force at this end, and it may add reduce here, but then this is obviously reversible in nature, so you may have to look at plus or minus, take into account the positive and negative signs, and you need to look at the shear force arising due to earthquake effect and combine it with the gravity load shear force, and then provide for the reinforcement, shear reinforcement. This entire shear force has to be withstood. So the shear force is shear due to dead load and live load, and there would be moment at end A, as you can see here, moment at end A plus moment at end B divided by the clear span. So that gives you the constant shear, and that's the shear. And when I say these moments, these are the over strength, right? So beam end moments accounting for the over strength. So it is the accounting for the over strength. So whatever is our estimate of over strength, so this would be typically whatever we arrive at from the elastic analysis from the demand, that would be some amplification factor times the elastic moment that we compute, and that needs to be taken in the calculation, because in no way there is simply failure, shear failure is to be avoided at all costs. No matter what it takes, we just do not allow shear, I mean the beam to fail in shear before it develops flexural plastic hinge, because the shear failure is going to be brittle and all of a sudden, and it is going to lead to a catastrophic failure. So shear failure is to be avoided at all cost, and that can only be done. The sentence is rather dramatic, but it is achieved very easily by accounting for, I mean, how do we avoid shear failure? By providing the adequate shear capacity. And how do we provide what is adequate shear capacity? We estimate what is going to be the maximum shear that can ever come across, that may ever come up on the beam for resistance, for developing resistance against. And that can only happen because of, I mean, there is a fairly straightforward way of calculating this shear force due to gravity loads, and obviously this will be with incorporation of appropriate load factors. And then the moments, because of the earthquake effects, so end moments in the beam, which and because of the earthquake effects, and those need to be amplified. Elastically computed moments from the approximate analysis, they have to be amplified to account for whatever is the overstrength, and obviously the appropriate load factors will of course come in again. And divided by the length, and that is the shear force that has to be withstood. Now this shear force obviously is a overestimation, because overstrength, we have already accounted for overstrength. So this is the largest shear force that can ever come up on the beam, and if we provide reinforcement, shear reinforcement, I mean this entire thing has to be withstood by the shear reinforcement in the plastic zone region. So in plastic hinge region, entire shear resistance should be provided by shear reinforcement. And how do we achieve that? If we know that this is the total shear, then obviously the shear stress, average shear stress is going to be V by BD, and this has to be, this defines the if Fy yield stress in the shear reinforcement, then this is given by total area of steel for shear is given by tau multiplied by Bs divided by Fy, and what else? Yeah. Right, so this is the beam width, and S is the spacing between the stirrups, and Fy is the yield stress of the steel, and this is the area of steel that is required, that is provided cross section area of the steel reinforcement. for shear reinforcement, right? And obviously, in order to achieve, I mean, the not less than stirrups should not be smaller than 6 mm diameter. So minimum diameter is of course 6 mm, but maximum diameter is of course limited from practical considerations. As the diameter increases, it becomes that much more increasingly difficult to bend it into appropriate uh, shape for in the form of ties. So maybe 6 mm or 8 mm is or at most 10 mm. You can't really go more than that, and shear reinforcement has to be decided on that. So depending on what is the spacing, so spacing is generally kept at 100 mm or 1/4 of the beam depth, whichever in the plastic hinge region. And of course some part of the I mean, you can these are approximate numbers. You can find out the appropriate guidelines in IS 13920. Right, and this has to extend over the plastic hinge region. As we discussed, that plastic hinge region would be about 2 times the effective depth. That's the plastic hinge region that for which this kind of special ductile detailing has to be adhered to. And in the middle, if that is the elastic region, then this spacing can be relaxed, and some contribution from the resistance of the concrete in resistance of shear can be accounted for, can also be incorporated, and that will lead to uh, increased spacing of the stirrups, and that will lead to some uh, more spaced out placement of the stirrups, and that you can see in the detail, the spatial ductile detailing that is only applicable near the ends, and you will see that the spacing gradually increases uh, beyond the plastic hinge length. And again, as you approach the end, then on the other end, then again the you approach the another plastic hinge region, and you need to account for again provide this special reinforcement. I mean, the entire shear stress, entire shear strength has to be provided by the shear reinforcement. Concrete strength cannot be relied upon in the plastic hinge region, and again you go back to closer spacing, and also the bent up bars for providing resistance against sliding shear failure. Right, so that pretty much takes care of the design of beams. Rest of the usual principles of reinforced concrete design of course continue to apply. uh, the only change in the earthquake resistant design that brings in is the providing a hierarchy of failure, and encouraging a particular mode of failure in the flexure zone, and then knowing that this is allowed, then what are the consequences, and avoiding the other failures that may happen, that may be triggered because of that, and trying to provide capacities more than the forces that are coming on because of the flexural failure that will be triggered during design earthquake in elastic deformation, and also in the case of the MCE, the collapse, the maximum earthquake that can happen. Even in the most severe case of earthquake, we should the column, the beam capacities should always be such that the shear failure never happens, right? So that way it will, I mean, there are a lot of conservatism that goes in these numbers, and that will actually help in avoiding shear failure even in the case when very severe earthquake uh, hits the region. Similar considerations actually work for the design of columns. Again, as we said in the beginning, when we looked at that small toy model about the effect of hinges developing in the columns and beams, then we saw that the consequences of development of hinges in the columns are very, very disastrous. It instantaneously loses the vertical load carrying capacity. On the other hand, if the hinges develop in the beams, the structure continues to support the gravity load, and there is no instantaneous threat to the stability of the structure, and therefore we derive that inference from that example, that column capacities, flexural capacities of the column have to be greater than the flexural capacities of the beams that frame into the column, and that gives us the number, again going back by the same overstrength factors. The column capacities have to be based on the overstrength on the beam capacities that are framing into the column, and those have to be accounted for using the overstrength. So accounting for overstrength, so the column moments have to be based on the overstrength estimation, and typically that overstrength factor usually comes to around 1.3 to 1.5. Very rarely it may, if you do a very rigorous analysis, it may actually sometimes go up to 1.8 or 1.9, but it is rarely feasible and rarely uh, worthwhile to go into the very detailed analysis, and an approximate factor of 1.3 for computing the column moments is generally adequate. So as we say, sigma MB so sigma MC should be greater than 1.2 times sigma MB. That's what is recommended in IS code, and when we say this sigma MB, then obviously this sigma MB has to account for the overstrength of the beam moments, just to be on the safer side, because absolutely it is not uh, possible to tolerate any kind of hinging developing in the mid-story columns. There is obviously, it cannot be avoided, the hinges plastic hinges at the support. Ground floor columns cannot be avoided, but at top end and at all upper floors. Columns should not develop plastic hinges. Now that comes, herein comes a very crucial thing. This is what is, how do we ensure? We can definitely ensure this by using the capacity design technique, capacity design principles. We find what is the maximum moment, as I said, incorporating moment over strength. Right? So, if we already accounted for whatever is the possibility of overstrength that can happen, and that is the absolute maximum that can happen from any possible configuration, any possible case, and then we find out what is the moment of the column that has to be greater than this, and that's how we provide the capacity. Then obviously the moments developed in the column will always be less than their elastic limit. So then there is no possibility of developing plastic hinges, and then the fallout of that is, why should we then provide spatial confining and ductile detailing in the columns? If you look at IS 13920, the spatial ductile detailing provision, this closed spacing, the confining steel is not only for the beams, even the columns you have to provide for this ductile detailing, right? So we can, if we are sure, if we can eliminate all possible sources, then it is indeed possible to avoid to relax the spatial confining reinforcement steel in the columns, because we will not be required to provide excessive curvature ductilities in that case, because if the columns are not developing inelastic moments, then large curvature ductilities will not be required, and it is possible to probably, it is possible, not probably, it is possible to relax the spacing requirement. But, and whatever you save, you can actually provide in the making the beams safer and more ductile, and that can actually take care of the complete system. But very often it is not possible, or just as a matter of caution, we try to be little more cautious in our approach, and particularly in the case of very severe earthquake, uh, we may not be able to guarantee that uh, moments in columns will not exceed the elastic limit, and then the plastic hinges may develop, and some amount of curvature ductility is again required, and that is why you have that 13920, the reinforcement detailing, confining steel, special ductile detailing in the columns, also figuring there. Although, in my opinion, it is possible to avoid that if we can figure out what is the maximum moment that is that a column has to withstand, and provide design accordingly. Then we should not be actually having to worry about ductile detailing for the columns. But so far, as long as we adhere to the code, nobody questions. If you deviate from the code, then obviously there are going to be lots of questions, and you need to be ready with logical explanation. I mean, there is nothing. I mean, you can always deviate from the code. It is possible for you to deviate from the code if you can provide your decisions, if you can support your decisions with a logical argument, and based on calculations. So if you can do that, it may be possible to save little bit on the transfer steel in columns, but it's probably too much of a hassle, and it's probably much easier and much quicker to just adhere to ductile detailing provisions in the code, and go ahead with it. But nevertheless, you should always adhere to the moment capacities of the columns should be greater than uh, code says 1.2, but I would be more comfortable with 1.3. But anyway, so that's what the moment capacities, and again the shear capacities should again I mean, all these column moments, they come from only from the beams. If you see this, so the moments in the column, they would be the the column, this moment at this joint, the moment in the column at this point and at this point would be defined by the moments in the beam at this point and at this point, right? So these are the beams framing in, and these are the I mean, if we know what are the maximum moments in these beams, then we can find out what are the columns that we need to provide for. And obviously the column capacities will have to be will depend on the uh, moment capacities of the two floors. I mean, this is the joint, and you need to look at the moment capacity of the column below the joint, and also the moment capacity of the column above the joint, and together they will provide the resistance against the moments that are transferred from the beams. And obviously column design is a little more complicated because of the axial force that come onto it. So axial forces, not only because of the gravity loads, there would be axial forces because of the I mean shear force on the beams because of the earthquake load. They would be transferred as axial forces to the columns, and those have to be accounted for in the uh, uh, interaction diagrams, and the moment capacities for the column should be computed from accounting for the axial loads, total axial loads that come onto the system, right? And again, shear force, obviously we already worked out, and shear force is, again, if you provide this special ductile reinforcement, then it very much pretty much takes care of the shear strength requirement. But again, we need to uh, adhere, uh, provide 45 bent 45-degree bent shear reinforcement to avoid sliding shear. And also one more thing, this is obviously for the, no hinges being formed, allowed to develop, is of course valid for the intermediate floors. As I said, plastic hinges at the bottom of the ground floors as columns are possible, and also plastic hinges may be allowed to develop in top floor. And if we allow plastic hinges to be developed, then obviously it becomes much simpler, and reinforcement details are also requirements are reduced because you are allowing inelastic deformation to happen. So you can afford to reduce the reinforcement and allow uh, longitudinal steel to be to yield. Now, why is this allowed in the top floor? First thing is, at the top floor, it is possible to achieve large curvature ductility even with very little reinforcement, very little confinement, obvious, because there is not enough axial load to support. So the capacities are moment capacity, because of the presence of axial load, is not severely hampered in the top floor. So it is possible to develop plastic hinges in the column without uh, compromising the structural stability of the building, right? So plastic hinges, in if you allow it in the top floor, not much harm is comes to the building as such, this stability of the structure, and that may lead to some saving in the reinforcement detailing. So I'll stop here. Any questions?